Time now?
Yeah.
Yep. Did you get my He has to finish his course.
Oh. Whenever you're ready.
Okay, I guess so. What time is it?
5:02.
Okay. Bueno, no sé si vieron el video. ¿Ya han visto el video? Sí, pues está bien. Por eso me pongo aquí, porque el otro día estaba acá y nada más salía mi brazo. Se oye bien, se escucha bien y creo que se ve bien. No he visto todo, nada más una parte. Pero una cosa que sí tenemos que hacer, él tiene que repetir las preguntas porque pues no se escuchan. Entonces, si preguntan algo, él va a repetirlo para que se grabe. Hoy, bueno, vamos a seguir con la introducción de Ben y se va pues ya a meter en cosas un poco más de profundidad. Y luego, después del descanso, con las galletas y todo, tendremos a Kathleen Skiro, quien va a hablar sobre su tema de disertación doctoral. Okay. Y de nuevo, si tienen preguntas, cualquier cosa. Volvió Pietro, entonces yo voy a traer todas las materias, los artículos y eso que están en las referencias, y, lo traigo mañana y subimos las notas que Ben ya completó. Okay. ¿Alguna duda, pregunta? Am I forgetting anything?
I have no idea what you just said.
Okay.
I heard my name a few times. So.
Okay. All right, Ben. What I do with coffee?
Over there on the table. All right, so welcome back to day number 2, Physics of Tropical Convection. I think maybe we should all stand up and do some jumping jacks to warm up. I have some coffee, so I'll be okay. So what we're going to do today is talk a little bit about the theory, some theories for understanding tropical convection, and we have a kind of two-part approach today. So I'm covering the first part, which is sort of the development of some basic ideas in radiative convective equilibrium and convective quasi-equilibrium. And then in part 2, Kathleen will talk about a kind of another theory or another framework for understanding tropical convection in terms of statistical mechanics and self-organized criticality, and also in the course of that share some of her research results. I'd point out my email address. A couple of people emailed me questions from yesterday, which is good, so if you have any questions, please email me if you don't ask them during the lecture. And I also, on my website, I posted what I call a beta version of Lecture 1, beta meaning there might be errors in it that I will have to correct, but you can go there and download a PDF, and I'll do the same thing for this lecture tomorrow and so on and so forth. Also, by putting it on my website, maybe you'll go and look at my research page and download some of my papers. Kathleen's email address is also up here. So what I want to start off with today is just to kind of remind you of what the temperature structure of the atmosphere looks like. Of course, you remember from Introduction to Meteorology that the atmosphere is divided into layers. The layer that most of us are interested in this course is the troposphere, the lowermost 10 to 15 kilometers, which is characterized by, most of the meteorologically relevant things that we're interested in, like deep convection. And what we observe in the mean is a decreasing temperature with height. Remember, we defined lapse rate yesterday as the negative of dT dz, So this corresponds to the positive lapse rate. And then in the stratosphere, we have an inverted profile. So actually in the stratosphere temperature, the temperature increases with height. Then we have these other structures up above. So what we're interested in looking at is what determines this temperature profile, particularly in the troposphere. So just to kind of remind you a little bit of some basic physics of radiation, because that's kind of a relevant issue here. We want to discuss a little bit about the thermal emission of an object and the idea of the Planck function. So essentially the Planck function gives us the functional dependence of energy emission per unit area, per unit time, per wavelength for an object of temperature T. And so when you see a plot like this, it's basically showing you the energy per unit area, per unit time, essentially per unit wavelength, as a function of temperature. So each of these curves is for an object at a different temperature. So if we're talking about an object of the surface temperature of the sun, we kind of have this emission profile. The peak of the emissions profile for the sun is in the visible part of the electromagnetic spectrum. We could also plot the Earth on here. The Earth has a temperature around 300 Kelvin, so that would be, way down here at the x-axis with a peak in its profile that would be shifted into the longer wavelengths. So that's the functional form of the Planck function, which really isn't important for our purposes, other than to say that from this function, if we integrate over all wavelengths, and we have, in this case, essentially what I want to do is develop a simple radiative balance for a planet, and starting with the case that the planet has no atmosphere, just to kind of develop the basic framework. If we take that Planck function from the previous slide, integrate over all wavelengths, and multiply by the surface area of the planet, assuming the planet has a radius r, then the emission, the watts per meter squared, power per unit area, is given by this quantity F, which is a fourth power of temperature as a consequence of the Planck function. So this, if we consider this planet, say it's Earth, the emission here that we would get in watts per meter squared depends on the mean temperature of the Earth. All right? So what we also want to consider is how much energy the Earth is intercepting from the sun. And so we can define this function, which is the absorbed solar radiation at the surface of this planet, and that depends on solar flux density, which is essentially how much energy per unit area per unit time is crossing the orbital path of the Earth, times the sort of cross-sectional area that the Earth presents to the sun, assuming it's plane parallel. And then this 1 minus A here is the albedo, or the reflectivity of the planet, and so this just tells us, some fraction of it is absorbed, the rest is reflected. So if we have this planet in thermal equilibrium, then this emission as a function of the temperature of the planet has to equal the absorbed shortwave from the sun. And from that, we can derive the emission temperature of the planet, which is this expression here. And then if we go ahead and we plug in parameters appropriate to the Earth, you find that the emissions temperature is 255 Kelvin, minus 18 degrees C. Compare that to the observed temperature of the Earth, it's about 33 degrees Celsius, or 33 Kelvin, too low. Okay? But here we've assumed that this planet has no atmosphere. So if we think about what happens in the presence of an atmosphere, of course the Earth has an atmosphere that consists of a mixture of constituents. The most plentiful by volume are molecular nitrogen at about 78%, molecular oxygen about 21%, and then a whole bunch of other constituents at much smaller percentages by volume. But things that you'll notice here like CO2, which account for, and it's increasing as a function of time because we're putting more CO2 into the atmosphere, and of course that's what we think about when we talk about the global warming problem. But in its kind of natural state, the fact that the Earth has this mixture of gases and they're interacting with the radiation basically gives us a natural greenhouse effect. And how we understand that is if we look at the absorption of the atmosphere as a function of wavelength, you see that it has a fairly complicated structure as you go across from short wavelengths, UV, visible, to longer wavelengths, near IR and far IR. that we have this so-called solar window, which is essentially a kind of low point in the absorption profile of the atmosphere. So essentially it's a window, it's allowing wavelengths at that, it's allowing energy at those wavelengths to pass through. We also have this atmospheric window over here, which is at longer wavelengths. That's also transparent or largely transparent to the radiation in this part of the spectrum. And so we can take the sort of net effect of this absorption profile and we can reconstruct the model, again, a simple model, radiative balance, now considering a single layer that's kind of perfectly absorbing. So if we do that, we can essentially repeat the analysis from the no atmosphere case, but now we have to distinguish two layers. So the first layer, which would be at the top of this perfectly absorbing atmosphere, is just like the case we considered previously. So the incoming solar is balanced by the outgoing long-wave radiation as a function of temperature of the atmosphere. And so that gives us exactly the same temperature that we got before. The temperature at the top of the atmosphere would be 255 Kelvin. But if we look at what happens at the surface of the Earth, now we have, because of the solar window, the incoming shortwave radiation essentially passes through the atmosphere, and there's some absorption, but most of it reaches the surface where it's absorbed. That gets released in the form of longer wavelength radiation because, again, the surface temperature of the Earth is around 300 Kelvin. So that's going back out. And if we assume that this atmosphere is perfectly absorbing in the wavelengths that this outgoing long wave radiation is occurring, essentially all of that radiation gets absorbed here. Then some of it goes out as outgoing long wave radiation at the top of the Earth, but we also have, because this has two sides, we also have long wave radiation coming back down to the surface of the Earth. And so really when we do the accounting to find the surface temperature of the Earth, we have to account for both of these inputs. And if you do that, solve for the surface temperature of the Earth in this scenario, you would multiply this temperature at the top of the atmosphere by this power of 2 to the 1/4, and then you get a surface temperature that's 303 Kelvin. So now, in this perfectly absorbing atmosphere, we've overcompensated and made the surface of the Earth too hot. But you can see the effect demonstrated here. So of course, what we do in reality is we treat the atmosphere with its full vertical structure, taking into account compositional differences and so on as we move up and down, and you can do a kind of line-by-line integration through this spectrum to kind of account for the peaks and valleys. And what you get as a result of this full radiative transfer calculation would be temperature profiles that look like this. So what we're assuming in this kind of simple model is that all we're doing to determine the temperature profile of the Earth is to assume that it's being set by radiation, okay? So if you do that, you get, sorry, the curves are hard to make out, but you get this curve here, which corresponds to what's called pure radiative equilibrium. So that's when we assume that, again, that the temperature profile of the Earth is just determined by radiation balance. And so what you find in this pure radiative equilibrium calculation is you get still much too warm surface temperatures compared to what we observe, and in the upper troposphere you get much too cold. And that's, if you think back to yesterday's lecture, we have this dry adiabatic adjustment. So if you just looked at what the temperature profile would look like as a function of height, assuming it's dry adiabatic, what you find is that this pure radiative equilibrium case is actually steeper than dry adiabatic. And so what that tells us is this, from this pure radiative equilibrium calculation, that we have an unstable profile in the troposphere. Now it turns out, just as an aside, this kind of radiative transfer calculation actually gives us a pretty reasonable structure for temperature in the stratosphere. Okay, so that tells us to first order in the stratosphere, the temperature profile is largely set by radiation. But we have something else going on in the troposphere, and that something else turns out to be convection, okay, as kind of the dominant other process that's contributing to setting that temperature profile. So, as we were discussing yesterday, the vertical transport of heat in convection, that's essentially what convection is doing. And from the perspective of this radiative transfer calculation, you can think that radiation is causing the temperature profile within the stratosphere to become unstable, and convection is essentially counteracting that instability, okay? And so this is kind of this sort of radiative transfer calculation is sort of the simplest thing we can do. So the next thing we can do is consider what's called radiative convective equilibrium. And that's essentially where we redo a calculation like in the previous slide, but instead of having only radiation setting the temperature profile as a function of height, we also allow some form of convective adjustment to redistribute heat from the surface up. I'm sorry, this actually looks kind of washed out on the screen, but this is from a calculation that was done by Adam Sobel at Columbia using a one-dimensional single-column model with a convection parametrization tuned to give a reasonable temperature profile at the equator, but then essentially doing that calculation as a function of latitude on this axis. And so by accounting for the effect of convection, and this is done, we'll talk a little bit more on Thursday about convection parametrization, how that's actually implemented. But by including the effect of convection, we can get a reasonable, I mean, you can't really see it here, but a reasonable profile of temperature along the equator. Now, one of the things you'll notice if you follow this calculation poleward is the zero isotherm kind of crosses the 1,000 millibar, the surface essentially at about 35 degrees north latitude. Now, I live poleward of 35 degrees north latitude, and our annual mean temperature is above 0 degrees C. So what this radiative convective equilibrium model, what this calculation tells us is that we're still missing something, okay? And essentially what we're missing here in this kind of calculation is we don't have a large-scale redistribution of heat by the atmospheric circulation, all right? So that kind of adds another layer of complexity, which we won't really talk about. But the fact that we don't see such cold temperatures in high latitudes is a consequence of the redistribution of heat by the atmospheric and the ocean by the general circulation, okay? The nice thing about these kind of radiative convective equilibrium models is they allow us to predict certain things. So in this particular example, we can use the radiative convective equilibrium model to predict the height of the tropopause, so essentially where we see this, the sort of break between the troposphere and the stratosphere up above. They've also proven to be very useful tools for looking at things like the effect of, adding CO2 into the atmosphere as it warms, kind of looking at the hydrologic cycle response, at least in a kind of one-dimensional way, okay? So it's just to say that if you look at the literature of radiative convective equilibrium, you'll see a lot of applications to these kind of interesting problems. So I'm going to turn now, we can sort of think of radiative convective equilibrium as kind of the 0th order model for how, for what convection is doing, how convection is responsible for or contributing to setting the temperature profile in the atmosphere. We want to try to develop those ideas a little bit further. And so I just wanted to remind you of, this kind of schematic that we discussed yesterday. So if we think about this as kind of a diagram of temperature as a function of height, kind of from observations, we might have a profile that looks like this. So you see over the depth of the troposphere, this general decrease in temperature as we go up. In the stratosphere, the increase with height. And then we kind of develop the idea of kind of parcel theory to tell us what would happen if we took a parcel, lift it dry adiabatically up to its LCL, and then follow a moist adiabat, and then we can define these convectively relevant quantities, convective available potential energy, which again is the positive part of this buoyancy, or the positive buoyancy part of this profile, and the convective inhibition, which is the negative buoyancy part. And so this is kind of the way people often think about convection in terms of, convection as I say here, convection as events, okay? So if you think about the situation of, how we often look at convection, or we're interested in looking at severe weather over summertime mid-latitude continents like the Great Plains of the US, this is kind of the sort of structure that we're looking at. We have a large amount of CAPE available that can drive convection, but it needs to be overcome by it needs to overcome this convective inhibition, or this negative buoyancy region. But as we mentioned yesterday in the tropics, things things look a little bit different than this. We tend not to see such high values of CAPE or convective inhibition, at least, especially if we're talking about the oceans. Now, over land, we might still have situations like this, but over the ocean, we tend to see an atmosphere that's frequently quite close to moist adiabatic and neutral stability. So in other words, the temperature profile in the observed atmosphere would be closer to this moist adiabat. And as a result, you have lower values of CAPE and lower values of SYN. So that kind of leads to another way of thinking about convection, and that's convection as a statistical equilibrium. And I'll talk a little bit more about what this means, but essentially the idea is that we can think about convection in a statistical sense, and from that develop a notion which we call convective quasi-equilibrium, or CQE, and we understand this CQE concept in terms of this observed behavior of the tropical atmosphere being close to moist adiabatic and neutrally stable. So given this kind of observed tendency, all right, the underlying notion in this kind of statistical equilibrium view of things is that whatever convection is doing in the tropical atmosphere, it's doing it to kind of maintain this neutral stability, this moist adiabatic mean profile, okay? And also that we have a connection between what's happening at the implicitly small scales of convection. You know, if you think about convection in thunderstorms being on the scale of, you know, kilometers to tens of kilometers, compared to larger scale processes, and we'll talk a little bit more about scales as we go on. But with these kind of notions in mind, very famous paper now by Arakawa and Schubert was developed back in the mid-1970s that basically took these ideas of this notion of convection as a statistical equilibrium, and really what they were interested in doing in this paper was to try to use this as a basis for what we call the convective closure problem. We'll talk a little bit more about convective closure when we talk about how we represent convection in models on Thursday, but essentially for now, convective closure refers to the necessity in coarse resolution models, and by coarse resolution models, I mean models that have grid scales that are, you know, say 100 or 200 kilometers. In those models, it's not possible to represent explicitly these small-scale convective events. So in the sort of modeling language, we refer to that as subgrid scale. So the convective processes are implicitly subgrid scale. We have to have some way of relating those subgrid scale convective processes to what we can actually resolve in the coarse resolution model.
Okay.
Yep.
I don't know if you're going to talk about this at all, but how sensitive this idea of kind of an equilibrium profile is actually to the parcel that you choose in the thermodynamic path you choose. Thinking of kind of Carey Emanuel's neutral buoyancy idea. If you include freezing, there's a lot of caveats.
There are.
You might want to repeat that.
This is, yeah, so Dave's question was, you know, what, if I can kind of paraphrase, you know, essentially what about the complications due to effects that maybe this type of convective quasi-equilibrium doesn't deal with? And I guess I'll say that I'll talk about some of those things.
Okay.
All right, so this is kind of the setup of the problem. Now, you know, again, the motivation, Arakawa and Schubert's motivation for doing this was this kind of very pressing problem of being able to represent convection in coarse scale models. But it turns out to have inspired this whole kind of theoretical, this whole sort of theoretical development over the past 40 years of convective quasi-equilibrium. So, Akio Arakawa, I'd just like to show his picture. And I like this. So in 2010, Professor Arakawa was awarded the Wilhelm Bjerknes Medal. I think that's is that a WMO? It might be a WMO. You know, it's like the Nobel Prize of Meteorology. And I like the citation. You know, he was recognized for his pioneering and fundamental contributions to physically based discretization techniques in models and representations of convective clouds in models, and continuing work to bridge the gap between resolved and unresolved scales. I mean, he could have gotten the Bjerknes medal for doing any one of these things, but he did all of them. And I think it's really, if you know anything about modeling, when we discretize differential equations on a grid, that discretization approach, people talk about Arakawa grids. So, he was really, if you're talking about modeling anything in the atmospheric or climate system, if it hadn't been for Arakawa, who knows where we'd be. But I want to focus here on the work that he did in Arakawa and Schubert, along with Wayne Schubert, in the 1974 paper, and that's really how to kind of represent the problem that we face when we look kind of at, a patch of the tropics. We see a whole lot of structure in terms of the cloud field. We can't represent each individual cumulus congestus or, these cumulonimbus back here. We have to try to aggregate the effects within sort of the, again, coarse scale, 100 to 200 kilometer resolution. So how do we kind of capture all of that physics and do it in a faithful way? And so what Arakawa and Schubert introduced is the idea of a cloud population. And so that's essentially that we can discriminate or distinguish between different cloud types based on different characteristics of the cloud. So we might look at cloud types based on how tall the clouds are. We might look at other thermodynamic characteristics. But essentially, we want to try to group clouds with like characteristics together, and then think about, leading into the next slide, think about an ensemble or a sub-ensemble of convective clouds. So an ensemble here, that's just a type of, that's a fancy word for average, essentially. We want to treat the average effect of different cloud types, okay? So what Arakawa and Schubert did is introduce a quantity, lambda, which denotes the sub-ensemble of convective clouds. So we can have, a number of sub-ensembles. And again, a sub-ensemble, clouds within a sub-ensemble are distinguished by some common attribute, such as, how high the cloud tops are. From that, we want to think about representing two quantities, the vertical mass flux, m sub lambda, and the buoyancy, b sub lambda, which would be the, essentially the mass transport within this particular type of cloud, lambda, and the thermodynamics in terms of the buoyancy, okay? And what we want to do then is think about this kind of relationship between what's happening at the convective scales, at the implicitly smaller subgrid scales, and relate that to what's happening at the large scale, okay? So what Arakawa and Schubert did, and I'm kind of maybe introducing this in a somewhat backwards way, but let's think first about what's happening at the convective scale. So I'm going to define a derivative here, which is a derivative of some quantity a sub lambda. I'll talk a little bit more about what a sub lambda means, but just a time rate of change of this quantity with a subscript c, indicating that this is something that we're considering at the convective scale, okay? And essentially what we're doing here, the quantity that we're setting this equal to is related to the product of the buoyancy times dz. So remember from our discussion yesterday, buoyancy times dz integrated in the vertical, that's like cape, but then multiplied by this mass flux, m sub lambda. So again, it's, sorry about the poor quality here, but we're integrating this quantity then between cloud base and cloud top. And again, these limits of integration would be chosen for the particular type of cloud that we're dealing with. So if we have deep clouds, this value would be higher. If we have shallow clouds, it would be lower. And this quantity a sub lambda then is something that Arakawa and Schubert called the cloud work function. Cloud work function, you can think of that as, if you think about what convective available potential energy is as a potential energy, it's an energy that could be converted into kinetic energy of updrafts. So this cloud work function is really related to the kinetic energy of convection. At some level, it's more about the conversion of potential energy to kinetic energy, but it's telling us something about how much convection we can do as a result of well, let me jump ahead and get to the second line, which is the second part of this approach is to think now about what's happening at the large scale. So we can define again, a sort of analogous quantity here, a derivative of this cloud work function, but now represented at the large scale. And what we have here is the term F sub lambda, which you can think of as a production, it's a production term. So essentially we have large-scale, in this kind of view, we have large-scale processes that are producing energy to drive convection, and what the convection is doing, because we have an overall minus sign here, would be consuming the energy that's being created at the large scale. It turns out there's a slight complication. We have this large-scale production, which you can think of as kind of given by the external environment to the cloud, but then we also have kind of an additional term here, which represents the capacity or the ability of different clouds, different sub-ensembles to interact with one another. And that's going to basically modify the energy that's available for convection. So those interaction terms could be things like this. If you have, if we think about two different types of clouds, a tall cloud and a short cloud, and they're both growing, they're going to be interacting with the environment. So the effect of this growing tall cloud over here causes a warming of the environment that this shorter cloud over here experiences. So that's going to modify the energy production in this ensemble of clouds over here, and vice versa. The growing of these small clouds is going to have a warming effect on the environment that's going to modify what the clouds over here are seeing. The net result of this type of interaction would be to decrease the amount of energy available for convection to occur. You can also have an effect like this, which is a tall cloud that's growing. Now, this gets a bit into the details of what actually happens during this growth process, but in this kind of simple model, we basically have this, you can think of this cloud as a plume that's kind of growing. It's entraining or bringing in air mass through the sides, and then when it reaches its level of neutral buoyancy, you basically have a lot of the cloud, a lot of the mass within the cloud is being detrained. And so that leads to a kind of moistening of the sort of layer at the cloud top. So for this type of cloud, because it's tall, when it moistens the environment up here, it's actually not seen by these shorter clouds. Conversely, though, when these shorter clouds are detraining moisture into the environment, that can actually be entrained by these taller clouds. So this type of interaction is interesting in the sense that there's an asymmetry in the interaction, that essentially these, in terms of this particular physical effect, these clouds wouldn't have any impact on this cloud, but these clouds would have an impact on these clouds. And again, it's because of in this case, the difference in cloud heights and where the clouds are detraining moisture. So the idea of convective quasi-equilibrium really comes now in the following statement. So if we assume this kind of equilibrium view, if we take the sum of the part of the cloud work function associated with the convective scale processes, add to that the part of the cloud work function associated with large scale processes, convective equilibrium would tell us that the total time rate of change of this cloud work function equals 0. So it's telling us that whatever production of energy we have at the large scale is essentially being immediately consumed by the convective scale, okay? And that turns out to be critical because it allows us to take this quantity F sub lambda, which again is the large scale energy production, and thinking about this in the context of climate modeling, this would be something that we can explicitly represent on the coarse scale of a climate model. So we can take something that we can explicitly represent and relate that to things that we don't know because they're happening at the convective scale, namely the mass flux. Okay? So we have this balance because of convective quasi-equilibrium between this term, which we know, and the convective mass flux, which we can determine by inverting this expression. Okay? Now, it turns out it's not, things are never as simple as they seem. So we know F sub lambda, but we also need to know something about the buoyancy production. So that requires us to make some assumptions. We have to essentially have a cloud model that tells us something about the buoyancy profiles. But given those two pieces of information, from that we can determine the mass flux. And from an operational point of view in terms of developing convection schemes and models, this is really the basis then of these what are now called Arakawa and Schubert type convection schemes. Okay? But again, I would point out, the determination here is non-trivial because it depends on also defining this cloud model and knowing something about the microphysics. Okay? So Arakawa and Schubert provided some observational basis for this convective quasi-equilibrium idea by looking at some observations from the Western Pacific. These were done by Michio Yanai, who was also at UCLA in the early 1970s. And essentially what they did was computed, the details here are not so important, but computed this cloud work function A, took its time derivative, and plot that as a function of the large-scale energy production on the x-axis. And so what this is essentially telling us is, relative to the sort of scale of the energy production, the time rate of change of the cloud work function tends to be pretty small, okay? And that's essentially what we want, in the sort of strict convective quasi-equilibrium. This quantity, A sub lambda, wouldn't change as a function of time, okay? So, to within the sort of scatter that you might expect because it's observational data, the fact that these points along the y-axis are close to the zero line here is essentially confirming, or at least consistent with, what has to be true if we want convective quasi-equilibrium to hold. Okay? Now it turns out from an operational point of view, in kind of looking at simple convection schemes, oftentimes instead of explicitly calculating this cloud work function, we use some proxy for it, so not quite equivalent to it, but it's simple to use convective available potential energy because it's something that's relatively straightforward to calculate. So in this kind of framework, we can use CAPE you could think about CAPE here on or the time rate of change of CAPE on the y-axis. And just to put this into some perspective, yesterday we mentioned sort of typical values of CAPE in the tropical atmosphere might be on the order of 1,000 joules per kilogram. If you look at the large-scale production of energy, namely through the fluxes of energy into and out of the atmospheric column, and you kind of integrate over a day, essentially what you'd find then is that the production of energy would be on the order of 4,000 joules per kilogram. So the fact here that CAPE values are much smaller than the sort of typical energy production on these timescales kind of suggests that, as soon as we start to build up energy in the atmospheric column, convection is kind of getting rid of it, and as a consequence, the kind of CAPE itself is relatively small and also relatively invariant. Now, as Dave pointed out, this kind of idea of convective quasi-equilibrium, although it's kind of become the sort of theoretical basis that we often use to understand deep convection in the tropics, especially in the tropics, it does have some limitations or some criticisms. I just kind of summarized a few of them here. The first one that we might sort of point out is the sort of idea of causality. So if we go back to what I started with, sorry for toggling back here, this kind of idea of convection as events. And this is, again, if you're like a lot of our students at Rutgers and you're going to go on the storm chasing trip this summer, what you're looking for is convective events, okay? You're, kind of looking for profiles that have large values of CAPE and conditions that can overcome this convective inhibition so that you see, really big thunderstorms and can take nice pictures to show your folks back home. But, in this sort of view of things, this kind of event-based view is very different from this kind of statistical equilibrium view. And so, in terms of this criticism, at least if you kind of read the way things are formulated in Arakawa and Schubert, the formulation of convective quasi-equilibrium is often understood in terms of large-scale conditions forcing the convection. And this is sometimes referred to or sometimes thought of as the thermodynamic analogy, which is essentially convection as the system of interest is responding to its environment, which is the large scale. But one could kind of pose, that the opposite might actually be true, namely that the convection forces the large scale. And in some of what I'll talk about tomorrow in the sort of interplay between convection and the large scale, I think this idea is certainly true, that you have conditions under which you might be able to say that the large scale is forcing convection, but the inverse might also be true. Now, I kind of, in kind of putting together this list, I think I refer to it on the next slide, there's a very nice overview article by Yano and Planck that kind of summarized the development of convective quasi-equilibrium over the last 40 years. And this sort of causality argument or criticism of convective quasi-equilibrium might not be such a critical one. It might just be a matter of how you really interpret what's going on. Maybe the more critical criticism is the second one, which is the lack of, and I have here in parentheses, evidence for scale separation. So this kind of view of convective quasi-equilibrium, the way Arakawa and Schubert kind of formulated the work function, is to think about what's happening on convective scales as being distinct from what happens on large scales. And this is both in terms of time scale. So convective events tend to be, or the thinking is that the convection itself is relatively fast compared to the evolution of the large scale. But how much should the convective scale be separated from the time evolution of the large scale? And I think if you think back to the result I showed yesterday with Holloway and Nealon's analysis of the moisture relationship to strong convective events, particularly when maybe you start to think about convective organization happening on mesoscales, then the sort of line between the fast convective time scale and the kind of larger scale maybe gets blurred. And that's also true, I think, spatially, that we can't really, at some level, we might be able to think in terms of what's happening at the scale of an individual convective storm or convective thunderstorm, but we see a whole range of scales of convection in the tropics. And so that kind of presents a challenge. And also, kind of in the sense of thinking about convective quasi-equilibrium as a statistical one, this kind of statistical view kind of comes out of the development of statistical mechanics. So statistical mechanics as a discipline in physics really tries to think about what's happening, with a distribution of molecules, where you have many, many molecules, Avogadro's number of molecules, and relating that to some macro scale property of the system. So in that case, when you're talking about translating molecular behavior to macro scale behavior, when you have 10 to the 23, or larger number of particles, then maybe this kind of statistical view, the statistical view is reasonable. In the case of what we're talking about here, if you think about the kind of domain, especially thinking back to how Arakawa and Schubert wanted to apply this in coarse resolution models, you might be talking about the sort of macro scale being the size of a GCM grid box, 100 kilometers or 200 kilometers. The convective elements within that GCM grid box might be, a kilometer or 10 kilometers. So if you think about how many of those convective elements might be within a particular grid box at any given time, sure, it might be a relatively large number, but it's not going to be large in the sense that we typically think about the statistical mechanics from physics. And so that kind of maybe challenges the idea that there's, that the domain, particularly in the context of the parameterization problem in models, that the domain size here really might not be, or the GCM grid box size might not really be large enough for this kind of equilibrium to be realized.
Also the idea of propagation adjustment due to gravity.
Right, so I'll get to that in the next slide. The other two criticisms here maybe should think of them more as limits on convective quasi-equilibrium. And the first one might be the sort of idea of how applicable is this kind of convective quasi-equilibrium framework to conditions over land and to conditions in the mid-latitudes. So again, thinking about the mid-latitudes and the kind of example that I was showing earlier, where it's, kind of very clear that some kind of trigger is required in order for the sort of conditional instability in the profile to be realized, that this kind of triggering in the statistical equilibrium framework is sort of happening continuously. And so when you're talking about mid-latitude convection or convection over land in the tropics, the fact that we have a strong boundary layer cycle, a strong boundary layer diurnal cycle, with convection sort of happening preferentially at some time of day, really sort of emphasizes this view that we need to think about the convection problem also in terms of the triggering. And that's really not maybe, the convective quasi-equilibrium really maybe isn't designed to kind of think about that triggering problem. The second point here is something that Kathleen will talk about a bit more in a few minutes, and that's the transition to strong convection. And I kind of mentioned this in yesterday's talk, that looking at these kind of high-frequency statistics relating, say, column water vapor or column moisture as a proxy for instability to convection precipitation seems to suggest a very clear onset threshold for the increase in precipitation as a function of column water vapor. And that sort of, in a sense, challenges the equilibrium view, where you might expect a smoother transition. Now, it turns out if you look, and this maybe gets to the slide here, which I think is a really nice schematic, again, from this nice review paper by Yano and Plant, which is to kind of, and there's a whole bunch of things on here that I haven't really talked about, but essentially what I've tried to do here is kind of take the ideas that were discussed in this review article as kind of interpretations of convective quasi-equilibrium, and then maybe some alternative viewpoints. And this one down here, self-organized criticality, that will be something that Kathleen will talk about. I'll talk a little bit more tomorrow about this possibility over here, which Yano and Plant call the free ride, but we call or other people call the weak temperature gradient. And then this other one is kind of an idea that was developed by Brian Mapes, which is more this kind of idea of activation control, kind of tries to build in this idea of triggering of convection, which again maybe isn't within the sort of traditional view of convective quasi-equilibrium. But I also wanted to point out within the kind of blue box here the sort of various ways that you might interpret convective quasi-equilibrium. So I already mentioned the sort of thermodynamic analogy, which this one, as I said, might cause a problem in the sense of, implying a cause and effect with a large scale forcing the convective scale. But there's maybe a kind of another way of looking at things, kind of borrowing from what we tend to do in dynamics in the mid-latitudes and, kind of consider balanced dynamics like geostrophy or quasi-geostrophy. And that's really to think maybe about convective quasi-equilibrium more in the sense of a balance. And in that sense, if you're thinking about it more in the sense of a balance, then the direction of the causal arrow doesn't really matter so much. And it turns out, and I think tomorrow we'll kind of show this, I think, particularly nicely, that in the context of this sort of free ride alternative, you can actually, in some limit of this, you can actually get to this sort of balanced dynamic view of convective quasi-equilibrium. Now, Dave had pointed out a kind of another thing which maybe is not so much an interpretation of convective quasi-equilibrium in the sense of Arakawa and Schubert, where they kind of have this formal requirement that the cloud work function, the time rate of change of it goes to 0, but to maybe kind of relax that, to sort of relax the time scale over which that process occurs. And so this has kind of led to an extension, if you will, of the sort of original Arakawa and Schubert to what we call convective adjustment. And in the sort of convective adjustment framework, you would essentially think about the same sort of thing here, but instead of having, this thing, or if you use CAPE instead of cloud work function. Instead of having this be strictly equal to 0, you'd kind of relax that. This turns out to be slightly problematic because it requires that you introduce a time scale for that convective adjustment process to occur. And it turns out if we look, and many people have been looking for that time scale for quite some time, and there's sort of a wide range of convective adjustment timescales. I mean, some people speculate it's on the order of a couple of hours. It could be, up to a sizable fraction of a day. And when you start talking about some of the things we were mentioning yesterday in terms of the spatial organization of convection, like in mesoscale convective systems, that maybe also challenges this idea, so that a kind of typical thing, if you're kind of familiar with the literature on convective parameterizations, a very common one kind of in this convective adjustment framework is the Betts and Miller 1986 convective adjustment scheme, which is essentially to relax temperature to some convectively defined reference profile over some time scale. And, again, the question is what is that time scale, and what in the physics determines that time scale? From a modeling point of view, you might imagine, if you run a climate model with for models that kind of have this convective adjustment scheme, a simple thing to do is to vary the convective adjustment timescale and look at the sensitivity of the simulations. And it turns out if you do, there's been some nice work that was done attempting, to sort of optimize the solution of climate models based on the value of this convective adjustment timescale. And it turns out if you try that optimization approach, it doesn't really constrain in any meaningful way what the value of that should be. So I think that's really the challenge kind of with this viewpoint, that we don't have a fundamental way of defining that time scale. So the final thing I wanted to talk about today is we're going to, and in this part, we're going to assume that we can think about convective quasi-equilibrium, but keeping in mind that there are these caveats about how applicable it might actually be. But to think, and this is kind of in anticipation of what we're going to do tomorrow, is to think about what the implications of convective quasi-equilibrium are in terms of our understanding of tropical thermodynamics, and then tomorrow tropical dynamics. So we want to, for this kind of analysis, we want to think about, instead of the cloud work function as we think about in Arakawa and Schubert, instead think about the convective available potential energy. So remember, Cape, again, is this integral over the buoyancy field from the LFC to the equilibrium level. So we can recast this buoyancy for this analysis in terms of, instead of the density of the environment and the parcel, in terms of the specific volume. And instead of integrating over the vertical coordinate z, change it to pressure coordinates. So it just makes things look simpler. So if we imagined convective quasi-equilibrium holding, and Cape is kind of our proxy for the cloud work function, then in the limit where convective quasi-equilibrium holds, if we take the time rate of change of Cape, that should be equal to 0. So taking the time rate of change of Cape setting equal to 0 tells us that the integrand has to be equal to 0. And so from the vanishing of this integrand, we can do a bunch of manipulations based on some fundamental thermodynamics. So first let's look at the time rate of change of alpha, and again, the unprimed alpha here means that we're looking at this from the parcel point of view. It's the specific volume of the parcel. And we're going to, can't really go through the detailed thermodynamics here, but transform this time rate of change of the specific volume of the parcel using a powerful type of relationship that emerges in thermodynamics called a Maxwell relation. It basically allows us to recast that derivative in terms of another quantity that's maybe more thermodynamically relevant than the specific volume, and that's the moist static energy, actually the saturation moist static energy. But basically we can relate that derivative to a derivative of this quantity S star, the saturation moist static energy, and then multiplied by this factor which comes from the Maxwell relation, that's the vertical profile of the temperature. S star here, that's just the definition. Then if we look at the other term, which is the time rate of change of the specific volume of the environment, we can just apply the hydrostatic relationship. It looks a little bit different than the way we wrote the hydrostatic relationship yesterday because we're working in pressure coordinates, but it's essentially alpha is just minus the derivative of this geopotential function with respect to pressure. So just bear with me. So this, in order for convective quasi-equilibrium to hold, essentially we substitute in those derivatives. The term in the square brackets has to vanish, okay? Now, the vanishing of this term in the square brackets allows us to rewrite, we can actually do the integral with respect to pressure and set that equal to 0. So this second term on the right-hand side, if we just integrate in pressure, that just gives us the difference in this geopotential, which is essentially the potential energy per unit mass. The difference in geopotential evaluated at the LFC minus the geopotential evaluated at the equilibrium level. And this first term, we can relate using an assumption here that the saturation entropy, which from what we discussed yesterday, you can recast that in terms of a related quantity, the equivalent potential temperature, that if we assume that that's conserved following ascent through the cloud, then if we know the value of the equivalent potential temperature in the boundary layer because it's conserved, that allows us to determine that quantity as a function. I mean, it's the same value as a function of pressure, so we can essentially pull that out of the integral over pressure, integrate just this part which depends on temperature, and that just gives us a difference in the temperature at the LFC minus the equilibrium level. There's a lot in here. This is from a paper by Kerry Emanuel, David Nealon, and Chris Bretherton in 1994, which is kind of the, it's like the Bible of applying convective quasi-equilibrium arguments to try to develop our understanding of tropical circulation. I've read this paper several times now, and every time I find something that I didn't know before. But essentially, the result of all of this gymnastics is to have a relatively simple relationship between the time rate of change of the equivalent potential temperature in the boundary layer and this term over here, which if you know the hypsometric relationship, this is what we call the thickness. The thickness of the convective quasi-equilibrium convective layer, so essentially how deep the troposphere is above the boundary layer to which it's coupled. And that thickness you can kind of think of in sort of a qualitative sense, the thicker the convective quasi-equilibrium convective layer, the deeper the convection, the stronger the convection. And so what this tells us is if we know how equivalent potential temperature in the boundary layer is changing as a function of height, then we know how the thickness in the atmosphere above the boundary layer is changing as a function of height. And so this, to a large extent, in the tropics, tells us that predicting or understanding the response of the boundary layer, I think Emanuel et al. Formally call it the subcloud layer theta E, but it's essentially the boundary layer theta E, allows us to determine how convection is responding to the disturbances that are producing those fluctuations in theta E. So we can kind of summarize then that relationship allows us to cast the question of the controls on convection in the tropics in terms of the controls on theta E in the boundary layer. And Emanuel et al. Kind of go through a kind of analysis to tell us how the equivalent potential temperature theta E in the boundary layer depends on things like the downdraft mass flux, theta E in the layer in which air is being entrained or mixed from the free troposphere up above into the boundary layer, theta E that's basically being produced as a result of fluxes at the surface, and another term which is proportional to radiative heating. Essentially, this kind of gives us a prescription for determining how these different contributions are affecting theta E in the boundary layer. So to kind of follow that through, if we look at theta E in the boundary layer, we can ask how a change in any one of these terms would change theta E. So for example, if we think about relative if we compare a state of cold sea surface temperature to a state of warm sea surface temperature, all other things being equal, that should give us a higher value of this theta E sub s term. That would increase theta E in the boundary layer. Increasing the surface wind speed, that actually would increase this coefficient, which is like a surface drag coefficient. So for all other factors being equal, if we increase surface wind speed, giving us a higher value of this of this parameter, that would also increase theta E in the boundary layer. You can see that the effect of the downdraft mass flux, typically the downdrafts are bringing in cooler and drier air into the boundary layer, so reducing equivalent potential temperature. So if we have some process that's modifying the theta E kind of in the part of the environment in which the downdrafts are being formed, so maybe you could think if you have a kind of cloud that initially develops and forms downdrafts, that it's going to entrain dry air in and bring that into the boundary layer. But then with subsequent growth of clouds, it's going to start to moisten the environment up here, and that would tend then to moderate or increase the theta E of the downdraft. So in that sense, that would also increase theta E in the boundary layer. So I think the take-home message here is that in this one of the kind of ways in which we can use this idea of convective quasi-equilibrium, apart from being able to represent convection in models, is to use it as kind of a basis for understanding, or interpreting how we expect convection to change to different kinds of disturbances or different kinds of ways of modifying sea surface temperature, wind speed, etc. Okay? So I think with that, we're at about an hour, so maybe it's a good time to break and...
If I could maybe just say a couple of things.
Yeah. Do you want to use the microphone, or?
I don't know if it's on.
Just because I think there were a few issues to close.
Is that on? Oh, okay. Yeah, I think it's always good to have the criticisms of this kind of quasi-equilibrium view. Again, just kind of following Carrie Emanuel's idea. Sorry, Carrie, if you're watching this. I'm not trying to criticize you. If you consider the atmosphere, the tropical atmosphere, moist, neutral, it's very critically dependent on which parcel you choose to lift in the atmosphere. So it also depends very critically on whether you choose to do it reversibly, which he tends to do, or whether you do it sort of adiabatically. If you lift a very near surface parcel and you do it sort of adiabatically, you tend to get even pretty large capes in the convectively active tropical atmosphere. If you do like Carrie tends to do, grabbing just the subcloud layer parcel and lifting it, it is close to moist neutral. So you agree with that?
Yeah, I think that's fair.
So considering that's a very critical basis of kind of the idea of moist neutrality in the atmosphere, that convection works to keep the atmosphere moist neutral, well, that seems that might be open to question whether that's really true, at least looking at it from the thermodynamics. If you just want to say, all right, what controls what? If you take radiative convective equilibrium, the tropical belt, yeah, radiation controls everything. It's a one-directional thing. The other issue would be the kind of the scale separation you were talking about, that the atmosphere can actually be adjusted very quickly by gravity waves, and that was the thing that Brian Mapes was pointing out. So it's hard to say whether convection is a small-scale phenomenon or it's actually could have some large-scale aspects to it.
Well, I think, yeah, and I think tomorrow when I talk about WTG, that's really part of it. Really, I think the other side.
Okay. I think it's always good to include the critics. Now, I think Kerry Emanuel's great, and I think his ideas are great, but it's also good to look at the other side of the people who have criticized what they've developed.
I think that's fair, and I think the review article that I mentioned in the slides by Yano and Planck, I think they do a good job, kind of presenting the historic development and the development of these criticisms, the different interpretations of convective quasi-equilibrium So I'd recommend, obviously, looking at that for more detail.
So we'll upload that article, the Yano and Plant. And also the Emmanuel 1994 is just, it's a classic.
Yeah, but I
And-
had that on the list.
Oh, do you have it on the list? Okay, and then the critique of that one is also from Bjorn Stevens, who's now the head of Max Planck. And so you can look at their perspective of why they think that kind of the Nealon and Emmanuel idea is not necessarily the most accurate view of tropical convection, large-scale interactions. So we can, huh?
Well, so not to mention too, like the kind of Raymond, sort of boundary layer QE as opposed to applying throughout the depth of the troposphere. So I guess I think a good message here is that this topic is 40 years old, but I think there's a lot that's still here to be explored.
Right. And one of our favorite subjects and something we talk a lot about is, and it's something he just mentioned, is how the vertical profile of water vapor actually plays into the convective cycle. So when you take it away from thinking about just CAPE and SYN energetics, but also think of the water vapor, that could actually have a very serious consequence for the nature of the adjusted atmosphere.
Yep.
So I guess what we can do is cookies and coffee and then keep going with Kathleen, if she's ready. Okay. So, I don't know, 10 minutes maximum?
Yep.
Do you want to say anything, Karen?
No, I don't know.
I thought this thing went off after a while. I guess it stays on.
Yeah, I'm sorry, when you were asking that, I don't think I was quite following at the time.
Okay. No, that's normal. Also, Okay, sure.
It was saturation entropy, but you're calling it moist static energy on one of your slides. I didn't say anything, but the one there, that one. Saturation entropy.
Is that the saturation? Yeah, you're right, it is the saturation entropy.
But you said it in the next one. So I didn't.
Okay.
But I didn't say anything.
Yeah.
So the ABL, this is
Oh, yeah.
Have you guys met?
Yeah.
No.
I think you asked a question yesterday.
Yeah, I asked it. So the ABL is like, you were talking about a little bit the height of the ABL, and it's somehow like proportional or has a relationship with this convective activity.
Oh, the thick, no, so it's actually the layer above,
The layer
the
above.
free troposphere essentially.
Yeah, so, well, okay, so then, now the other question is like, so what regarding the height of the boundary layer?
What controls the height of the boundary layer?
So, like, usually, like, radiative forcing is what controls the boundary layer height. Therefore, that's mainly the reason why we don't have, like, I don't know, my wife is from Iceland, but you never see convective. These towers in Iceland.
Well,
The boundary layer is really shallow there.
so again,
Is it like,
and you can kind of interject here, but I mean, I think it's really this view that that this is kind of a statistical equilibrium view that really kind of hides. It really sort of hides the issue of how convection actually develops.
Yeah.
I mean, it's more a statement that you have this. If you think about radiative convective equilibrium as kind of the simple example, that radiation is destabilizing the atmosphere. It's kind of producing the energy available for convection, and convection comes and eliminates the instability. But how, the time evolution of that process, which is, really where the boundary layer kind of comes in. How you actually go from a non-convecting state to a convecting state. I think this kind of framework is silent on that. I mentioned in this, and I think this is kind of brought out nicely in this review article, this kind of view of activation control as kind of an alternative.
Yeah.
I mean, that's sort of Brian Mapes's argument that you need to think about what's doing the triggering.
yeah, the nucleation?
Well, or, I mean, particularly if you were thinking about this as kind of, I have this set of observational soundings looking at a convective event over wherever. that kind of event-based perspective really isn't consistent with the quasi-equilibrium, which is, again, more about what's happening in sort of a statistically integrated sense.
Yeah.
I don't know if that answers.
Yeah. It's the point of view from the statistical. I think. Yeah.
I was mainly, I mean, you know, I would say this has become, convective quasi-equilibrium has kind of become the dominant paradigm in understanding tropical convection. And I think in part because of people like Harry Emanuel kind of pushing it then to, you know, the problem that tropical meteorology has faced sort of relative to mid-latitudes is we don't have nice things like geostrophy or quasi-geostrophy as kind of balanced dynamical formulations that you can sort of, I mean, that still doesn't deal with the time evolution problem. I mean, you just run a numerical weather prediction model. But to kind of think about what the physics are doing, it's nice to have a balanced kind of model. And what I'll talk about tomorrow with the free ride or the WTG as kind of an example comes out of this kind of idea that maybe convective quasi-equilibrium is more of a, that it's more of this kind of balanced dynamics view.
And may I swap you out?
Oh, yeah.
I want to see if I knew a couple of your things weren't showing up, and I put some light gray text
I think
in there,
that's,
so
yeah,
I want to see if I need to bold it or something.
I'll have to pay more attention to that tomorrow. So.
Our thing at UCLA does that too. Oh, never mind.
I don't know if you want to use the little clicker thing or.
Yes, I would love to. Well, does it have a pointer on it?
It does.
Okay, then I would love to.
You can use it independently of the clicker. But, so if you plug this thing in,
Oh, I
you
see.
can advance the slides.
I usually do it this way,
Okay.
so I'll keep it like that. But perfect. Okay. Now how do I? Assuming this goes over.
A little bit on.
Okay. Thank you. Here we go.
Nope.
Okay. I don't like it when it does this.
Yeah, I think probably if you just if you go to the slideshow, it should probably just fill up. Or are you doing this? Yeah, it is PowerPoint. So.
I want to quickly look to see if.
Oh, yeah.
See, I want to bold this a little bit more so it shows up.
Let me, what is this?
Oh, sorry, that's my computer thing. I just need to make a couple of things darker because they didn't show up. I think that should be okay, though. Let me... Aha, that's better.
Let me just say 1 or 2 words about you. So I know you're doing your PhD. You did a master's where?
It's just part of my program at UCLA.
Oh, it's like all the way.
Yeah,
Okay, so
yeah,
where'd you
yeah.
do your undergrad then?
Johns Hopkins. Right.
Brad, Johns Hopkins, and then do you want me to say anything in particular of interest? I mean, you're like, what year? You're in your year?
Yeah, my last year.
Last year.
That's fair, even though I'm kind of not. I'm in my almost last year.
It's
It makes me sound more.
Yeah, it's flexible year. Anything in particular interesting?
I think that's good.
Okay. Did you know how to order the chain and everything?
In a minute. Actually, I'm not sure which one is mine. But that's okay. I'll just drink one of them.
Did something bad happen? Oh.
There we go. It's just touchy. You may want to warn them that I might go a little over.
What's that?
I said you may want to warn them that I might go a little over.
Oh, okay. Maybe, yeah. Okay. Bueno, pues les quiero presentar a Kathleen Skiro. Parece que es Shiro, pero es Skiro, ¿no? Okay. Ella sí estudia español, ¿eh? Así que cuidado con lo que digan, ¿no? Como ya hemos dicho varias veces, está estudiando con David Nealon de UCLA. Está en su último año de su doctorado. Hizo su undergraduate, su licenciatura en Johns Hopkins y está trabajando ahora en algunos artículos. Y yo personalmente le agradezco mucho porque está usando mis datos de la Amazonia y yo he estado rogando muchos años para que gente como Nealon y esas personas usen, y a través de ella y ven si ya los están usando. Y pues les tengo mucho, ¿cómo se dice? Aprecio y cariño y todo, ¿okay? Bueno, entonces, ella dice que a lo mejor tarda un poco porque no sabe exactamente cuánto tiempo se va a tardar, pero no hay problema. Ok, ¿hasta las 9? Okay, thank you.
Thank you. Yeah, so today I'd like to speak a bit about this overall theme of criticality, which is actually a statistical mechanics term and is used widely in statistical mechanics. And I'd like to talk about how that relates to tropical precipitation. It's something that I'm very interested in. I think it's a really cool topic. I think it's a really great theory. And so I want to go step by step and kind of outline how we define criticality, what a phase transition is, what a continuous phase transition is, and how that relates to precipitation, namely tropical precipitation in the climate system. So a little bit about what's on the menu. In order to explain how criticality relates to tropical precipitation, I first need to define it, and I need to speak about it and how it relates to phase transitions. Then I'll identify key features of critical phase transitions so that we can then identify them in the climate system and in tropical precipitation. I'll do that by presenting a classical example that some of you may already know, but I think it's a good way to look at criticality in general and understand the main characteristics that we'll be looking for. And then I'd like to define something called self-organized criticality, which is an extension of criticality, but to natural systems. And then I'll present evidence for self-organized criticality in deep convection and precipitation. And I also am appreciating this opportunity to discuss some of my own research and how this relates to both deep convection over tropical land and tropical ocean, and maybe some of the key differences. And then I'll end with some applications to modeling. So first, what is criticality? Well, the word critical is actually used in science in a number of ways, but here we mean it to be the critical phenomena studied in statistical physics in connection with phase transitions. Okay, so a phase transition, a change of a system from one regime or state to another, exhibiting very different properties. The one you all know is water. Water changes phases, gas to liquid to solid, and we call that a first order phase transition or a discontinuous phase transition. And a phase transition is characterized by a sharp transition in an order parameter, and I'll talk about an order parameter in terms of the phase transition to water in a minute to give us some context. And this order parameter either changes discontinuously, or first order, like I said, or continuously, and we refer to that as second order or critical. So a critical phase transition would be one that is continuous. And the order parameter either changes discontinuously or continuously as a function of what we call a tuning parameter, which I will define in the context of water, because it's what we're most familiar with. So in terms of the water phase transitions, your order parameter is density. For instance, if you change from liquid to gas, you are decreasing the density discontinuously across these phase lines. Tuning parameter, as you change temperature and pressure, you are affecting the density, the order parameter. So as you jump across these lines, a discontinuous phase transition occurs. So this is an example of a first order phase transition. Okay, so we've defined phase transition, we've defined first order phase transition. So what is critical phenomena? Critical phenomena is best described being at the order or the border of order and disorder that is largely susceptible to external factors and strong correlations, which I'll talk about those external factors and strong correlations later in the presentation, within the system itself. And as I said earlier, the critical phenomena occur near continuous phase transitions. So these are of second order. Which brings me to my first and most classical example, which is ferromagnetism. For some that may not be familiar, ferromagnetism was used basically to describe any material that could exhibit spontaneous magnetization or a net magnetic moment in the absence of an external magnetic field. And the spin of electrons in the atoms are the source of magnetism in materials like iron. And ferromagnets are most magnetic when there's no thermal motion, because that disrupts the alignment of the dipoles. So here, in this particular plot, we're looking at temperature on the x-axis and magnetization on the y-axis. And what you see is that as T increases from 0, thermal motion, or entropy, competes with this ferromagnetic tendency for dipoles to align. In other words, when it's colder, the dipoles look like this. They're aligned, it's magnetic. When the temperature heats up, past a critical point, they become disaligned, or the term for that is paramagnetic in this particular context. So this critical temperature at which this changes from an ordered state, in this case, to a disordered state, or ferromagnetic to paramagnetic, this temperature is called a critical temperature. I'll denote things that are critical by subscript C. So in this case, it's T subscript C is the Curie temperature, which is commonly referred to. And there's a second order phase transition, and the system no longer maintains a spontaneous magnetization. So it's a continuous transition. It's not like a phase transition in water where one is discontinuous. It goes directly from liquid to gas. This is a very sharp transition from, in this case, if I start at T equals 0 and go past the critical point or approach the critical point, you start becoming less magnetic because your dipoles are less aligned. So you start with a ferromagnetic state, and after the critical point, you move into a paramagnetic state. So a more disordered state. You go from order to disorder. And this occurs continuously along the approach to the critical point. So another thing I'd like to point out is that this is a power law. So this decrease in magnetization as you approach, or as you increase temperature, follows a power law behavior. And at the critical point, the order parameter, which is the magnetization, changes discontinuously, or it's discontinuous, dmdt, it goes to infinity at this particular point. So this is the first main characteristic of a continuous phase transition, where you have this power law behavior that is occurring in the most ordered state. So as you, for instance, decrease temperature, you are disordered. As you approach the critical point, you become ordered. At that point, the magnetization increases and follows power law behavior out to t equals 0. So this power law is something that we'll keep seeing over and over again in critical phenomena. Okay, so using this example to kind of characterize certain things in critical phase transitions that I'd like for us to pay attention to as we go along. Overview, critical phase transitions are where the order parameter changes phases continuously as a function of the tuning parameter. In the magnetization case, the order parameter is the magnetization, and the tuning function is the temperature. You're tuning the temperature to be either higher or lower, and the magnetization changes due to that tune. And while the average behavior, this is an important point, while the average behavior of the order parameter does not change prior to criticality, it can still fluctuate, meaning that approaching the critical point from t equals 0, for instance, your disorder, you're mostly ordered, but as you start to approach that critical point, there are fluctuations in that order, meaning you do start seeing some paramagnetic tendencies where you, there's fluctuations in the magnetism. And so those aspects of variability I'll actually be talking about a decent amount in terms of the precipitation. But note that this is a phenomena of a critical phase transition, where as you approach this point, there's a lot of variability in the system. The magnetization can vary greatly as you approach this critical point. And this is exactly what I just said, that fluctuations increase dramatically as the critical point is approached. And to put that in context, any small change in temperature, any small change in the tuning parameter as you approach the critical point can have a very dramatic change in magnetization, okay? Can vary very much. And this is actually a term I'm going to be using a little bit, which is called susceptibility. How susceptible is a system to changes in temperature? And near the critical point, this is also something I'll come back to, fluctuations can occur at all scales. And I'll talk about this as a process in which in the supercritical state, it is scale invariant. So I'm going to be talking about scales a little bit. But near the critical point, these fluctuations can occur at all scales. So that's something to keep in mind. Also, as the critical point is approached, spatial correlation either increases or decreases depending on which side of the picture you're looking at. But for instance, as the critical point is approached from the higher temperature case, and you're approaching T critical, your spatial correlation between the alignments of the dipoles will increase. And so we're going to be talking about spatial correlation and how that is related to these critical phase transitions a lot. And so this is something that I want to use in this context. Again, as you approach the critical point from higher temperatures, you see that your dipoles, which were paramagnetic or not aligned at all, no magnetization, start spatially conforming or becoming more spatially correlated as you approach this critical point. So that's one of the main characteristics of critical phenomena. And then another one that I mentioned was at the critical point, the order parameter and other thermodynamic quantities, which I'll define a little bit later, they diverge, meaning their derivatives become infinite. And then the behavior of that order parameter follows a power law distribution. In the paramagnetic case and ferromagnetic case, it would be out to t equals 0. So these are some key characteristics of critical phase transitions that I would like for us to keep in mind as we go along. And the main one being that the behavior of the order parameter follows a power law distribution after approaching and exceeding the critical point. Okay, so I'm talking about power laws a decent amount, and I'd like to define this mathematically and talk a little bit about it before I keep referencing it in the context of criticality. But as we saw in the magnetism example, power laws emerge at a critical point between phases. So a power law is given by the following form. I'm using an example over here, a very canonical example, where you have S would be the energy of an earthquake, and N as a function of S could be the number of earthquakes with that energy. And this is a logarithm plot. So the x-axis is in a log scale and the y-axis is in a log scale. Earthquake magnitude is by definition, a log scale. So if I take the log of both sides, you get log of, in this case, the number of earthquakes with a particular energy equals negative tau, which we call the critical exponent, times the log of the energy of the earthquake. And what we see is a characteristic straight line when you plot a power law function on a log-log axis. And so this is something we'll be seeing a little bit when I present results that indicate criticality and precipitation. And so I want us to be familiar with this. This is, by the way, called the Gutenberg-Richter Law, and it's a commonly known relationship between earthquake magnitude and the energy of the earthquake. So another thing that's very interesting about power laws that I'd like to present, because we'll be talking about it in kind of how it relates to precipitation, but why it's a really beautiful thing. So a key feature of power laws is that upon rescaling the independent variable, in this case it would be earthquake magnitude, the power law's exponent that defines the dependent variable remains the same. So in other words, power laws and critical phenomena are scale independent. An example of this, kind of a simple example, not related to precipitation or anything at all, would be, assume for instance we find that 2 kilobyte files in a computer are 4 times less common than 1 kilobyte files. Changing scales, we find the same thing in megabytes, that 2 megabyte files are 4 times less common than 1 megabyte files. I just changed this by a lot. The scale changed by a lot, but the relationship, 4 times less common, is still the same. Meaning that as you zoom in, or as you look at different scales, the relationship, in this case the power law behavior, shows that it's scale invariant. Okay, so back to the ferromagnetism example to round out a couple of more, or to talk a little bit about other physical quantities that we would observe or try to observe when we were trying to identify critical phenomena. This is the Ising model. This is a way to represent what I was trying to look at qualitatively in the ferromagnetism example. So this is still in the magnetism example. Another physical quantity that you would look at when you look at critical phenomena would be heat capacity, for instance. Looking at some variable of the energy and how it changes across the critical point. And so you'll find, or you should identify a critical point as where heat capacity or where energy diverges at the critical point. Another would be susceptibility. I briefly introduced this concept when I talked about variability around a critical point. So the susceptibility is, the name is chosen as such because it's defining how susceptible a particular order parameter is to changes in the tuning parameter near the critical point. In other words, how susceptible is magnetization to little changes in temperature near the critical point. Okay, so variability of fluctuations around the critical point. And this diverges at the critical point. So the divergence in heat capacity near the critical point, the divergence in susceptibility near the critical point, these divergences are key for identifying locations of critical phenomena and kind of asserting their existence. Another is correlation function. This isn't showing up very well, But basically, a correlation function describes a correlation with points at a particular distance, I'm calling here R, from a reference point. And so as you move away from a particular reference point, the correlation will naturally decrease. But if you are, for instance, in a disordered phase or above the critical temperature, this decays exponentially past a particular point called the correlation length. Again, you can't see it very well here, but the correlation length is defined as the exponential decay length of the correlation function. And so taking the case of above the critical temperature, you see somewhat of a power law dependence before this critical or correlation length. But afterwards, you see a sharp drop-off or a sharp decay in the correlation function. So as you move farther and farther away from a particular point, the correlation with that point decreases exponentially. Now, at the critical point, in this case, the critical temperature, you see that there's a power law distribution. This is log scale. And so we knew from before that the straight lines show a power law distribution. So at the critical temperature, the correlation function is a power law function, meaning that the correlation between points as you increase in the distance from that particular reference point decays as a power law, not exponentially. And below the critical temperature, meaning in the ferromagnetic phase when the dipoles are aligned, there is no correlation length, just as in there's no correlation length at the critical temperature, meaning at the critical point, the correlation length diverges. There is no exponential decay in correlation function when you approach the critical point and above, or in this case below, in low temperatures. There is no exponential decay in the correlations. So this is another thing that identifies critical phenomena. Yes?
Can I just ask a quick question? So when you say the distance here is in the context of the Ising model, distance would actually be like measured as the position of the spins?
Yes, that's right.
Actually, can you repeat that?
Yeah, so the question I had was just on the interpretation of the distance, say in the context of the Ising model. So it would be, at the position of one spin, and then you move, say, one spin away, and then to the next position, and so on.
That's right, thank you. So yes, in this case, if you're taking, for instance, a particular dipole and you're looking for the correlation between other points, you're looking at the spin of the atom to try and figure out whether or not it's aligned or disaligned with the other particular reference point. And so that gives us more context to explain that in below the TC, below the critical point, you see that they're all aligned, so their correlation with one another, there's never an exponential decrease when you move away from that particular thing because they're all aligned. It's ferromagnetic. So this is a simpler example, but a very good example, I think, of what happens to energy of a system near a critical point, what happens to the susceptibility or the variability, the fluctuations around a critical point of the particular parameter of interest, in this case, magnetization. And the correlation function, how the particular points in space are correlated with one another, and how they follow these relationships or power law functions, or in the case of being above or subcritical, how they decay exponentially as you move away from one another. Okay, so power laws, power laws, power laws. We're talking a lot about power laws. I want to say a few things about them. Basically, power laws portray a wide variety of phenomena. You can see power law behavior in a number of natural systems or things that aren't tuned. For instance, we just talked about earthquake magnitude, which is down here. You can also talk about it in terms of crater sizes on Mars or something, or needle frequency in a directory or a population of a city. A lot of different things in nature follow power law distributions. And so this has raised a lot of interest in the physics and statistical mechanics community about why exactly these are occurring in nature. And so I'm going to get a little bit into that in the next part when I talk about a concept called self-organized criticality, because these are systems in which you're not sitting there tuning the temperature to make the magnetization, that's a hard word, to make the magnetization change. So these are things that self-organize into this type of behavior. That's also, and we'll talk about this too, critical behavior. So I wrote down here, because power law phenomena are ubiquitous in nature or everywhere, it is theorized to be a unifying principle that underlines patterns in nature at all levels. So I'm going to talk about this in terms of a concept called self-organized criticality. But first, I want to do a quick overview of some of the things I already said so that we can take them with us when we talk about this in terms of tropical precipitation. So first, key characteristics of critical phenomena. Critical describes a system between order and disorder that is characterized by an extremely large susceptibility, which we defined, to external factors and strong correlation between different parts of the system occurring at all existing scales in the system. The first key characteristic is a rapid transition in an order parameter, in the case we now know, magnetization, as a function of a tuning parameter, in the case we now know, temperature. The second is, at criticality, certain observables, like susceptibility, the energy, these and the magnetization itself, they diverge. Their derivative becomes infinite. And beyond that critical point, in supercriticality, order is established at all scales. And power law behavior is observed in the order parameter and the correlation function, which helps it to be observed in the order parameter itself. And so this is something that we're going to take forward with us to try and identify critical phenomena in precipitation. Okay, so self-organized criticality is a particular type or theory of criticality in which I'll read this. In systems work, the control parameter and the order parameter are coupled. The critical point can become an attractor, and self-organized criticality results. That's a little bit wordy, but basically, it's a critical point in which the system organizes itself. There's nothing tuning it. For instance, in the magnetization example, like I said, there's no temperature change that you're tuning to create a particular paramagnetization or ferromagnetization, but the system itself organizes towards a critical point. And this concept was introduced by Bock-Tang and Weisenfeld in 1987, and they use the example of a sand pile. So if you're familiar with any of the literature, that would be the canonical example of self-organized criticality. And here, systems driven by slow, constant energy input tend to organize themselves into critical states where all scales are relevant, as I was saying. And the main key point, which I've now probably said a couple of times, but the evolution of the critical state occurs without any design from any outside agent. It's established because of the dynamical interactions among the individual elements of the system itself, hence the term self-organized. So self-organized criticality, which I'll abbreviate with SOC because it's a long term, can potentially explain some ubiquitous patterns that are everywhere existing in nature that we view as complex, including some of the rare and catastrophic events, such as a large earthquake or a big storm, things like that. So returning to the atmosphere. Now we have what we need to kind of interpret self-organized criticality in the system. And so, just briefly, the atmosphere is a slowly driven, highly susceptible system that can store energy in the form of water vapor and suddenly release it in rain showers, as Ben has been teaching us. And as we just learned, quasi-equilibrium refers to a balance between the slow, large-scale driving processes and the rapid release of buoyancy by moist convection. And so there is evidence, and I will present evidence, that the attractive quasi-equilibrium state is the critical point of a continuous phase transition. That may seem a little obscure at first, but I'll try and explain what I mean by that by various bits of evidence. Okay, so the general hypothesis. Convection and precipitation in the tropics can be described as a system which self-organizes towards a critical point and exhibits characteristics of a continuous phase transition. Okay, so one of the first earlier tests or things that the scientists have done to to observe critical behavior in precipitation, basically the climate system through precipitation, we looked at event size distributions. And this is work from Peters, Hartline, and Christensen in 2002. And what they did here was there's event size on the x-axis. This is, again, a log-log scale, so a power law would be shown as a straight line. The number density of rain events per year, and as a function of m, versus the event size itself, which is on the x-axis. And the event size is basically the volume per area of water from a particular rain event. And so they looked at rain events that occurred continuously for at least a minute and added up basically the water in the column. And that's how, or the water that was produced as a result. Excuse me. And so that's how they calculated the event size. And so what you see here is that there is a power law distribution in the event size of the precipitation events versus the number density, or the amount of them, per year. And this was kind of the first work to establish some relationship between precipitation in the atmosphere and the fact that it could be thought of as a critical process. And some other work is outlined to the left as well. Okay, so that was the first test. Now, looking at event sizes is good, and it illustrates a power law distribution, which is a characteristic of a critical transition. But instead of only looking at event sizes, it would be preferable to examine commonly used observables in the critical phenomena. For instance, using an order parameter and see how it varies as a function of a tuning parameter. And so that is what Peters and Nealon, Ole Peters and David Nealon, tried and looked at in 2006. And so in their particular study, they used column water vapor as their tuning parameter and rain rate as a function of the tuning parameter as their order parameter. And so before I go in and show a bunch of plots, this is from 5 years of TRIM microwave retrievals of both estimated rain rates and vertically integrated column water. And they're looking at the tropical oceans. So they're looking at areas between 20 north and 20 south, and they're splitting up the different ocean basins accordingly. So they'll look at the Western Pacific, the Eastern Pacific, the Atlantic, the Indian, and we'll look at how some of these characteristics may change in the different ocean basins. But what they did in the study was they conditionally averaged rain rate by a given value of column water vapor, which is shown here. So for every value of column water vapor, they binned rain rate that occurred at that same value of column water vapor and averaged those rain rates. Okay, so that's the rain rate value that's being shown here as a function of column water vapor. And I apologize, this is a little bit blurry. But basically what you observe, again, here is the x-axis, which is, for all intents and purposes here, it's a column water vapor. They rescaled it by a factor, but it's column water vapor. And your typical value at a transition point here would be around 66 millimeters. But again, this is rescaled, so. But what you see is as the tuning parameter increases, so as the column water vapor increases, you have an increase in rain rate that occurs with it. And this curve here is that precipitation rate and how that changes with the order, the tuning parameter. So what you see in this black line is this power law fit to the precipitation increase observed. So that's the first thing we identified as something, first, a rapid transition, Another thing was a power law. These things are characteristic of a critical phenomena. So, and that can be given by this equation here, where A is just a system-dependent constant, and B is a universal exponent, which we'll talk about in a little bit more context in a bit. But here they have this plot inlaid. I forgot to mention, too, that this pickup in precipitation, there's a green curve and a red curve. And the green curve is for the Western Pacific, and the red curve is for the Eastern Pacific. So they're comparing two different ocean basins here, in which the tuning parameter, as it changes, the order parameter exhibits a critical transition. And in this inset here, there's, again, the red is, well, green is Western Pacific, the red is Eastern Pacific, the blue is the Atlantic, and the yellow is the Indian Ocean. And so what you see is that these power law functions that emerge after the critical point, they exhibit the same critical exponents for all different ocean basins. And so this kind of introduces this concept of universality, where these particular characteristics are observed in a number of different systems. In this case, they're observed in different ocean basins. So that's the main takeaway from here, is you have this increase in precipitation near a critical value of column water vapor, and it exhibits power law behavior above that critical point. And the critical exponents that define this power law are the exact same, or virtually the exact same, across all four ocean basins that are being examined here. Another thing I'd like to point out that's on this plot is the precipitation variability. And if you remember, I defined fluctuations in an order. Yes?
Sorry for the interruption.
That's okay.
Does that mean that the onset of criticality is the same for all four cases? But the onset of criticality here, that 66, where the power law curve starts, how is that given?
That's a great question. So, oh, sure. So the question was whether or not the 66 millimeters was consistent across the ocean basins, and how the 66 millimeters was calculated. So the 66 millimeters is dependent, actually, on mean tropospheric temperature, which I'll show in a little bit. So actually, that precipitation threshold can change depending on the mean tropospheric temperature, because that affects the amount of column water vapor within the column at saturation. So that can affect the actual critical value of column water vapor. And the critical value of column water vapor here is determined empirically by the power law function. Yeah, thank you. So this curve here, as I was saying, is the precipitation variability. So here, in a little bit of a roundabout way, they define it in the text as the susceptibility. And if you recall, when I was talking about the magnetic system, we talked about susceptibility in terms of the fluctuations of the magnetism right near the critical point. And that behavior is also observed right here in terms of the precipitation variability, where you have a lot, or the most, precipitation variability right near this critical value, meaning that precipitation values can range from 0 millimeters per hour in these averages to 70 millimeters per hour in these averages. The precipitation variability is great at these particular points. So that, again, as we define as a susceptibility, and that's what's being shown here. Again, another key constituent of critical phase transitions. So, all in all, from just the first plot, you see there's strong evidence for critical phenomena and self-organized criticality. This is a bit of a complicated plot, so I'm going to try and, dive into it as simply as possible, but some scaling of the precipitation variance, as described in this paper, allows us to view this as a correlation function. So recall that I was talking about correlation functions before, how they decay as a power law above a critical point. In the magnetization example, when I had the three plot plots shown. And so here, different averaging intervals allow us to assess the degree of spatial variability. So what they did here was, again, this is satellite information. So this is a gridded product at 0.25 degrees, 0.5 degrees, 1 degree, and 2 degree. And when I say that, it's 0.25 by 0.25 degrees, or 0.5 by 0.5 degrees, et cetera. And so what they did here was they calculated different column water vapor spatial averages and precipitation spatial averages to see how robust these statistics were across the different spatial lengths. And, excuse me, so here, what's being shown is more or less, as they describe in the text, a correlation function. So as you reach this critical point, you see, with some variability, that there's a good, first of all, collapse of the correlation functions, meaning that at these different scales, they all exhibit the same behavior. And you see this behavior where you have this power law decay of spatial correlations as you increase column water vapor above the critical point. So this is strong evidence for the behavior of the system exhibiting scale invariance. So again, as you increase the scale, the behavior remains consistent. And I won't get too much into this, but I thought this was a fun point. In the paper, they say that mesoscale convective systems, which Ben introduced to us, this is evidence that they could possibly be long-range correlation structures that are kind of akin to critical structures beyond this critical point. So an interesting concept that, or at least I think is really fun and interesting, that can relate to precipitation both in time and in space, and can really put statistics behind its organization. So this is another plot that is really important to look at when we're trying to understand a little bit of the physics of the system, where here we have a peak. I'm going to walk through the axes first. So this is precipitable water, or column water vapor. Same thing, they're used interchangeably. And this is the number of occurrences. So these are distributions in green, for instance, of all observations, precipitating or not precipitating. The blue is the distribution of the precipitating points per value of column water vapor. Again, these are averages. And what you can, one of the main features here is that the system actually has the highest probability of being found near the beginning of the intense precipitation regime. So you see that the peak in the distribution is between 50-something and 60 millimeters. This is relatively high column water vapor. This is a peak right before, for instance, the critical pickup of precipitation with column water vapor. So this almost kind of asserts what we were talking about earlier with the quasi-equilibrium a little bit, which I'll get into in a minute. But the distribution here of all observations, something physically to kind of point out, is that say there's some large-scale forcing that comes and decreases the column water vapor value. You could possibly interpret this as the slow buildup of moisture in the atmosphere that is a much longer scale than would be this dissipation process that occurs as a function of the convection itself, where you're raining out the precipitation. It's a very fast dissipation mechanism versus the longer sort of convergence ramp up of moisture that occurs. So that's something physical to take away from this particular plot. And so the system doesn't remain at high column water vapor for long periods of time because it will then convect and precipitate out. So that's something physical to take away. And we'll talk a bit more about these distributions when I look at some more in situ observations. Okay, so in summary, a critical value of column water vapor marks a continuous phase transition to a regime of strong atmospheric convection and precipitation beyond the critical point, with correlated regions on with correlated regions on scales of tens to hundreds of kilometers, as we saw with the plot when you did averaging. And before, attention to critical phenomena was usually put in terms of event size distributions, as I showed in the first plot that really looked at criticality in the atmosphere, partly due to the difficulty of measuring standard observables, like column water vapor and precipitation. So basically other order parameters, tuning parameters, susceptibilities, et cetera. These are harder to observe. So in Peters and Nealon, which is the paper that I went through, we identify observables in a physical system that exhibit characteristics of critical phenomena. One of these being power law behavior at water vapor being greater than the critical column water vapor, increased susceptibility near the critical point, or increased variability in the order parameter near the critical point, and spatial correlation behavior. And of course, as we've gone through and defined, all of these behaviors suggest proximity to a continuous phase transition. Again, also, this system is self-organized. You're not tuning column water vapor to be a particular way. This is the atmosphere self-organizing itself into these phases, or into this behavior that we see. And we also saw in the last plot that there's a tendency for the system to reside near the critical point. And so that isn't inconsistent with the whole idea of quasi-equilibrium theory, but this theory that we're presenting is, as Ben was explaining to us, that these are departures from quasi-equilibrium theory. And so these properties become important when you're trying to parameterize convection, and using, for instance, in a stochastic way instead of a deterministic way. And so it's important to consider these departures from quasi-equilibrium when you're looking at convective parameterization. So a couple of more examples or evidence of self-organized criticality. This is a follow-up study by David Nealon, Ole Peters, and Katrina Hales in 2009. And so this is showing column water vapor and mean precipitation rate in millimeters per hour, as we were showing before. But now, this is just for the Eastern Pacific, but now the curves show for different mean tropospheric temperatures. Mean tropospheric temperature in this case means between 1,000 and 200 millibars, you average the mean tropospheric temperature. And so you have 268 Kelvin on the low end, 274 Kelvin on the high end, and you see that there is a dependence on this critical point and in this behavior on the mean tropospheric temperature. So as this temperature increases, your critical point extends out to high column water vapor, and it changes. So there are different aspects of these systems that can affect these critical phase transitions. And a main takeaway from this paper is, even though there are different things within the system, in this case temperature, that can affect these critical phenomena and the location of these critical transitions, when you, for instance here, rescale by the critical column water vapor, or in this case you're normalizing, you're taking the column water vapor divided by its critical value, and you see that they all of these curves that were once different, when you normalize them each by their critical value, they collapse very nicely onto this particular plot. And that kind of shows us that this behavior, it shows some great consistencies, universality perhaps, of this particular behavior. So even though this behavior can change based on temperature, the behavior within the system is largely consistent, universal. So to read this bottom punchline, the collapse of precipitation statistics validates the critical column water vapor as marking a continuous phase transition and determines universal properties within the system. And so this becomes particularly useful. It's a useful measure and statistic when you're looking at validating both model results and informing revisions to convective parameterizations, which we'll talk about in a little bit, and Ben will talk about more. I guess it's Thursday. And a little bit more about the distributions, because I'll be talking about this in my own work in a minute. Here, you see, here's the East Pacific. This is the distribution for all points. On the x-axis, you see the same that we just saw where the pickup curves collapsed, where you have the column water vapor normalized by its critical value. And the same down here. This is for all points, precipitating or not. This is for just precipitating points. And as we kind of alluded to before, there is this feedback between the order parameter and the tuning parameter that tends to return the system towards the critical region. And in this case, for a slowly forced system, in which dissipative effects are important only above the critical point, the frequency of occurrence tends to peak near the critical point. So you have this peak, actually nearly Gaussian peak in the distribution, right near the critical point. And then, as you approach the critical point, you have a sharp decrease due to dissipation effects of the counts in both the all points case and the precipitating points case. And this decline, of course, in the all points case is because of the precipitation in the precipitation points case. So you see a sudden drop in the frequency of occurrence across the critical region, and this is attributed to the strong dissipation occurring in the system through precipitation. And you see a long tail extending out to high column water vapor, which is useful from the modeling perspective to identify some of the extreme departures. Okay, so all these studies examine deep convection and precipitation over tropical oceans, which has been wonderful. We've gained a lot of information. There are a lot of great observations from satellites over tropical oceans. In fact, there are a lot of field campaigns that have been performed over tropical oceans, as Ben was mentioning on the first day. But what about tropical land? So these statistics have been produced over tropical oceans, but how does this behavior occur, or does this behavior occur over tropical land? There are a couple of complications to that side of the story, and one of them is that you can't, observations over tropical land are pretty difficult. Or I should say, continuous observations for long time periods don't exist very much, if at all, except for instance, an example that I'll show in a minute. But this is because the observations from the satellites over the ocean, their microwave retrievals, it actually does not work in the column water vapor over land. And so you miss this key part, the tuning parameter. You don't have that to observe over tropical land. And so this is actually an example that I've been working on from the Amazon, where I'll orient us a little bit. This is column water vapor versus precipitation. I apologize, this is not showing up very well. In the first plot, I'll talk about them plot by plot. And here, in the tropical land case, it's hard to create these, what I've referred to as convective onset statistics, because our observational record isn't very large, and we rely upon radiosondes and things rather than very continuous measurements over tropical ocean over many, many years. So in many ways, over tropical land, it's a bit more difficult to reproduce some of these statistics, but nonetheless, a lot of these relationships that we observed over tropical ocean still hold true over tropical land. And that's kind of what's exhibited here, where I'm using radiosonde column water vapor, consistent over 2 years. They're about 4 to 5 times a day. They're launched. And so the column water vapor is derived from the radiosondes, and the precipitation rate is taken from an instrument on the ground. And so this relationship is relatively robust in the radiosonde column water vapor. It's also robust when you look at a radiometer. The radiometer produces higher frequency column water vapor measurements. And so the precipitation measurements are very high frequency as well. So that's where you can get a lot more data from that and produce some more robust statistics. So here, where we might be limited by observations and looking out to higher column water vapor, in the radiometer, we have a little bit more data and can produce some robust statistics out to high column water vapor. So here in the land case, it's a bit hard, or I should say in any in situ observation case, when you're limited by observations, it's hard to validate, for instance, power law behavior past a particular critical point. Nonetheless, a transition, likely critical, is still very evident in this particular instance. these plots here are showing that as you increase column water vapor, you're increasing the percentage of precipitating points. And then this plot here is showing the distributions, which I showed a moment ago. So say the critical point, roughly speaking, would be right near here. Your peak in your distribution of both all points and precipitating points for both instruments, more robust for the radiometer because we have a lot more data points. But your peak in the distribution of both precipitating points and all points, including precipitating points, occurs right before the critical point. And then again, you see this behavior where you have a sharp drop-off due to dissipative effects of the system because it's precipitating out. You see this sharp drop-off in the distribution, and you see a little bit, although it's hard to say because we have limited observations, this long tail extending out to high column water vapor. So, and this is also shown, another great way to look at column water vapor over land is a lot of what Dave is doing, implementing these GPS retrieval sites where you can get reliable all-weather column water vapor information to produce robust statistics like this, because unless you have a field campaign like we did in the Amazon here, I failed to mention this is called Go Amazon. It's a 2-year continuous campaign over the Amazon. Very cool stuff. But the GPS extends this to many different places, possibly, and it's imperative for tropical land because we don't have any other continuous column water vapor measurements anywhere over tropical land because, again, the satellites cannot retrieve column water vapor over tropical land. So again, this is results shown from the GPS stations, or one GPS station in the Amazon for 3.5 years of data. And you do, again, see this pickup in precipitation that's characteristic of a critical phase transition. So evidence here, increase in precipitating points, and then your overall behavior in the distribution is very consistent with what we've been seeing over both tropical oceans and from the Go Amazon case. My last main point is that because we don't have incredible resolution of observations of column water vapor and precipitation over, from field measurements and field campaigns, we can see a lot of this transition in the precipitation as a function of column water vapor, but it also gives us a really important opportunity to look at the vertical structure of the column and how, for instance, relating physically. So we see all these behaviors, but we want to relate physically why high column water vapor can be a proxy for buoyancy, why high column water vapor allows for these higher precipitation events. So the main finding of Holloway and Nealon was that this is, the color bar is different values of column water vapor. The x-axis is specific humidity. So these are specific humidity profiles. And you see that here, the high column water vapor values are much higher in the mid-troposphere than they are for the lower column water vapor values. So there's actually a lot of variability between high and low column water vapor in the free troposphere, meaning above the boundary layer. And so the main takeaway from Holloway and Nealon in 2009 was that column water vapor is largely defined. Here it is, the pickup in precipitation with column water vapor for total column water vapor. And here it is when you split it up into an 850 to 200 column. You integrate it between 850 and 200 instead. And this shows that this largely this relationship is explained by this relationship, meaning the variability in the free tropospheric water vapor is what's explaining variability in the total column water vapor, which is a key finding. Very quickly, this is showing that this is relative humidity, this is pressure. Here in this plot, when you have high column water vapor, you're nearly saturated through a deep layer. So this is consistent with these more highly buoyant, highly convective characteristics. So now, again, we're looking at the vertical characteristics to try and understand why precipitation transitions to high rain rates, or it has that critical transition as a function of column water vapor by looking at how the column water vapor is defined in terms of its vertical characteristics of relative humidity, and in this case, theta E, where you have column water vapor values have much higher theta E throughout the entire troposphere than do even values that are slightly lower. So these types of physical characteristics can help explain the behavior that we see in these critical phase transitions as column water vapor increases. This plot is, we didn't talk much about virtual temperature yet, but for all intents and purposes, virtual temperature here, if it's greater than 0, it's positively buoyant. If it's less than 0, it's negatively buoyant. Here what we're trying to do, or what Holloway-Nealon, this is from Holloway-Nealon, so this is a site in the tropical Western Pacific. They took radiosondes, these are averages of radiosondes at higher column water vapor in the hotter colors and lower column water vapor in the lower colors, and they're trying to understand, again, why the pickup in precipitation occurs at high column water vapor. It should be physically because you have higher buoyancy. So here they are where they take a plume buoyancy calculation, and to make it realistic, they're entraining air, so it's interacting with its environment to a realistic extent. And again, you do see, consistent with the pickup in precipitation, that higher column water vapor, profiles with higher average column water vapor, certainly do have higher average buoyancies. So this puts more of a physical explanation to, again, what we're seeing with this particular pickup. This is some of my own work from a paper that should be published soon. And on the left is what we saw earlier with Holloway and Nealon. Well, we all saw all these with Holloway and Nealon for the tropical Western Pacific case. Ben showed you that little island the other day of Nauru. And so the tropical Western Pacific case that I was just showing was from that little island. And here, these are observations presented in the same way from the Amazon. So this is contrasting the case we just saw and the vertical profiles we just saw over tropical ocean to the case over tropical land. So here in A, this is, again, I apologize, this isn't showing up very well. This is specific humidity versus pressure, relative humidity versus pressure, theta E versus pressure. So you see that, again, here, just as in the ocean case, most of your variability is being explained by variability in the free troposphere. So your specific humidity is varying much more greatly in the free troposphere, although there is some variability in the boundary layer, as one might expect over tropical land. Same with B, where your higher water vapor cases, higher column water vapor cases in the hotter colors, exhibit saturation through a deep layer, as would be expected. So this is consistent with the pickup in precipitation, again, with the highest variability in the free troposphere, but there is some variability in boundary layer relative humidity that's helping to explain variability in column water vapor, which is slightly different from the ocean case. And here, again, the theta E, which is another variable that we look at for buoyancy. And these don't show up very well, so I'll make a brief comment about them, that when we look at the same virtual temperature plots over land versus ocean, there are some key differences. Again, this is virtual temperature difference versus pressure. Virtual temperature difference here, without defining it for all intents and purposes, if it's greater than 0, it's positively buoyant. If it's less than 0, it's negatively buoyant. These profiles were taken from the radiosondes, but there was a plume calculation that is determining this buoyancy, including mixing with the surrounding environment. So the red, which you can barely see, would be your high column water vapor case, and every other case in between. The plot I showed you in the tropical Western Pacific was for all times. The radiosondes were at local noon and local midnight. Here we have radiosondes launched at 5 times a day. And as we've learned a little bit, the difference in land versus ocean is kind of stark in terms of the boundary layer dynamics and the diurnal cycle. So there are certain phenomena that occur throughout the day over land that don't occur over ocean. One of which is SIN, convective inhibition that occurs in some of the nighttime hours. So if you go about trying to explain the pickup in precipitation you observe with these realistic plots of buoyancy, as one would want to, you have to keep in mind that a lot of these nighttime soundings aren't convective at all on their own. And even in the highest water vapor cases, unless something is coming through sometimes and breaking through that convective inhibition, you wouldn't get convection in these nighttime hours. A lot of the convection over land occurs midday. And so that's kind of what we're seeing here. Again, it's hard to see, but the main point is that midday, you don't have any of this convective inhibition that you observe at other times of day, namely the early morning and late evening. And a lot of the profiles shown here that you can't see are show that they would be convective, although some would be possibly shallowly convective, maybe creating some shallow cumulus, but not actually being deeply convective. If you could see a little bit more clearly, only some of the cases belonging to the higher column water vapor values would be deeply convective through a deep layer. So one thing to point out is some of this looks different from the ocean case, but to a first order, a lot of this looks exactly the same, meaning that at higher column water vapor, you have higher buoyancies. So that's a physical explanation for why we see the pickup in precipitation as it increases in column water vapor. Okay, my last thing, just a couple comments about applications to modeling. As Ben has mentioned a couple of times, many GCMs are insufficient, general circulation models or global climate models, are insufficient in capturing the occurrence of strong precipitation and precipitation in general in the tropics. Why? Well, for many reasons, some of which include the following that apply to what I have been saying. The first being deficiencies in the way precipitation is represented in the models. And Ben talked a little bit about this earlier, where he mentioned that traditional parameterizations follow quasi-equilibrium, meaning that they represent only the ensemble mean of the small scales as a deterministic function of the large-scale flow. So these disregard fluctuations arising at the small scales, which we're observing in some of these systems that need to be taken into account. So while the system's attraction to the critical point is predicted by quasi-equilibrium theory, several fundamental properties of the transition, including high precipitation variance in the critical region, they need to be considered. And so departures from quasi-equilibrium have motivated some revisions, but also stochastic, it's a hard word, convective parameterization. A couple of last comments that I talked about the variability in column water vapor being largely explained by variability in free tropospheric humidity. And a lot of the parameterizations are too insensitive to free tropospheric humidity. And entrainment, which you would see a relationship with free tropospheric humidity through entrainment, which will be described, I'm sure, later in the course. Entrainment assumptions used in a convection scheme certainly play an important role in its ability to stimulate the observed precipitation. And models without sufficient entrainment are shown to be less effective in producing general patterns of precipitation, but also on the smaller scale. And the reason we love these convective onset statistics is because they can be used to compare similar statistics produced by models. You can take model output and produce these same statistics to validate model performance in this particular fashion. How exactly? By directly comparing distributions of precipitating points, calculate the critical points, examine precipitation variability around a critical point. So all of these things can be done to look at the ability of a model to reproduce certain aspects of precipitation. My last thing, this is an example of that, an example of where you take model output and you compare it to observations. So this is an example from Sahani et al. 2012, and they used a GCM, an atmospheric GCM, at 0.5 by 0.5 degree resolution with a modified convection scheme that had sufficient entrainment. And they compared this to, here it's labeled as TMI, that's the satellite retrievals of instantaneous precipitation and column water vapor from TRIM at a slightly higher resolution. So here, column water vapor precipitation, CAM is shown in these, I can't even see. But anyway, you see these that show the power law distribution are the observations. These lines, these fits, are from the models. So there's a little bit of a discrepancy between the model and how it's reproducing the power law distribution, but the main characteristics of the pickup are observed when you see or when you use a model with sufficient entrainment. So when it, meaning that it shows a relationship between free troposphere humidity. It has a greater dependence on free troposphere humidity as well. So those are my main points, other than to say this research is important because it can inform revisions to convective parameterizations and the overall representation of precipitation in the tropics. Quick conclusions. So there's strong evidence for a critical phase transition in tropical precipitation at a critical value of column water vapor, as was shown from the evidence I presented. Another main point is that field campaigns allow for physical interpretation of these results by understanding vertical structures. So you want to understand where this pickup in precipitation comes from. Is it from increases in buoyancy or not? Is it physically represented or not? And Go Amazon is a great campaign to study this over land because it's a long, continuous observational record, which don't very much so exist on tropical land sites. And also GPS data is a great opportunity to take values of precipitable water, column water vapor, and examine these transition characteristics. Otherwise, it's hard to observe long continuous records of column water vapor over land. And lastly, these statistics describing the transition can certainly be very useful from a modeling perspective. So, thanks.
Very good. I had one quick question. Does anybody have a question? Ben, you want to?
Maybe just a comment.
Oh.
So, you know, the results that you're showing for Go Amazon, it's called Go Amazon. The Go stands for Green Ocean, right?
Yes,
So in a
thank you.
sense, maybe some of the similarity that we're seeing with respect to Nauru as a real oceanic site is maybe because the Amazon as a land region is sort of unique relative to other land regions. And I guess my point is maybe to plug the GPS, that, I mean, the observations that are being collected here in Mexico, that those might be interesting cases to look at too as another example of these statistics over a land surface, but that's not a green ocean.
Sure. Yeah, thanks.
If you didn't sign the lista, ¿no? Lo pasé por alguna parte. Sí? Oh, okay. Okay.
And I apologize for keeping you.
No, that was really, I thought that was really good, very informative, very clear, actually, very, very clear. One thing that just caught me, you were saying about the vertical structure being related to or the CWV, column water vapor, being related to buoyancy kind of controlling. But could there be another interpretation that has to do with precipitation efficiency? That is, moisture profiles in the atmosphere all things being equal, would tend to rain more, tend to be more efficient in terms of, and that would be also very closely related to entrainment.
Yeah,
And so that could be kind of another interpretation, not necessarily the correct one, but maybe another interpretation.
Yeah, I haven't thought too much about that, but I agree that it could possibly be.
Any preguntas, comentarios? Oh, yeah. A ver, no entendí. ¿Cómo fue?
¿Cuál fue el valor de beta que nunca lo vi en la...
What was the value of beta? The
For which
exponential.
system?
I guess probably just over for the rainfall over the oceans.
It's usually like 1.4 something.
Beta, isn't it like 0.2?
Oh, I'm sorry, yes, the critical exponent is like 1.4 something, but beta is usually like 0.25 something. I have to look it up, I'm sorry.
es que la mayoría de los procesos, de los fenómenos, en todas las leyes de potencia generalmente acerca de 2 negativos, más o menos, en todos los casos.
Okay, he's saying the general behavior tends to be 2, negative 2, the exponential is what he's saying in these critical systems.
It's closer to the radar. Actually, the radar equation that we're serving there, 1.4. I think they use the 1.4.
Okay. Related to column water vapor?
No, related with the radar equation. In the radar equation, they use that parameter.
Okay.
And that's a common range, like 1.25.
Yeah.
Arturo, do you have a question? No?
Well, I was wondering if the atmosphere, I mean, if we go into a global warming type of thing, are we getting closer to criticality? I mean, are we getting closer to organizing the tropics better than if we were?
That's a very interesting question. And
Let me
actually
repeat the
there's-
question. So he's saying basically under global warming, you're saying the critical, we would be getting, all things being equal, we'd be getting, pushing closer towards this critical value?
Well, we have
Of
more water vapor.
Water vapor, okay.
a great question, and actually being actively researched in our group. So I don't have any very specific comment about a result, but it's definitely a particular item of interest, and stay tuned.
Okay, well, if there's not any other questions, then I guess you're dismissed. We'll start again tomorrow at 5, and I think tomorrow night has been all the way through. Do you want to say anything about what you're going to talk about?
Yeah, it's coupling between convection and the large scale, so it'll sort of be some sort of general overview and then maybe a bit more of the research that I've done.
Okay, good. All right, thank you. That was good. That was really good.
Oh, thanks.
I thought it was really clear.
There were definitely points where, stuttering